Okay, now the mathematics involved in half-lives gets a little more intricate because unfortunately life is messy. You don't get nice percentages like 100% or 50% or 12.5 and on and on. So what happens when we don't get those values? What do we do about that? Well, let me introduce to you the world's worst bank. And this is the best way to think about it. Now, when you may not be familiar with this, you may be familiar with this, but let's get everybody on the same page, okay? When you put money into a bank, and you put it in a savings account or a CD account or whatever, you're going to get interest paid to you by the bank because you're giving them your money so that they can turn around and give that money to somebody else at a higher interest rate, so they pay you a little bit on the side. You have the security of knowing that it's insured, that if something happens to the bank, you still get your money. But at the same time, they're going to make a sizable profit off of your money, so everybody gets, what they want in the end. And the way that they do that, and this is not going to be important as to how we determine the half-life values for all this, but this is how it works. You put money into a bank. They put it through a formula. This is interest is equal to the principal, which is the amount of money you put in your bank, times 1 plus, then the rate, percentage rate. When I was growing up, the percentage rate was often between 4 and 6%. It's now around 1 to 2%. And divided by the number of periods of compounding, the compound interest. So like if you make a dollar on $100 in one time frame, then the next time frame it starts with $101 that they pay interest on instead of $100. It's not the same as simple interest, this is compound interest. So they have this formula taken to the nth power, where n is the number of times they break it up each year, times the amount of time or the number of years in which it's going to stay in the bank. Okay? Now, so like n is going to be 1 if it's a compound annually, 2 if it's an annually, 12 is monthly, so on like that. The highest one is infinity, which gets into calculus. You go to limits, and that is, if you can get a bank that's doing that, you're getting the biggest bang for your buck out of that. Just let me know. So any amount of money you make over a time frame is the interest plus your principal added together, or this monster formula right here. That's making money. That's a good thing. Now, the decomposition or the disappearance of a reactant with a half-life is, instead of gaining a percentage, you lose 50% per year, and it's compounded annually or time-lifeian or whatever you want to call it. So it's going to take your money, your amount of material, at a rate of 50%. So for every time frame, you're going to lose 50%. So your principal is now your A, your quantity, and times your original quantity times 0.5 to the n power. And remember, we were dividing by 2 to the n power, and the inverse of that for multiplication is 0.5 to the n power. So this is basically the same formula we had before, just written differently. So the longer you keep your money in this bank, the less money you will end up with. The money is symbolic for the number of grams of a first order reaction reactant. Okay? So let's take a look at some practice on this. The half-life of a reactant is 14.0 minutes. If you have 4.50 grams of this reactant, how much will you have in exactly 1 hour, and what is the value paid for this reaction? All right, so let's take a look at that. 3, 2, 1. Okay, so now let's put down what we know. We have half-life for this example, 14.0 minutes. The original concentration of A is 4.5 grams. And the time for this is 1 hour. Now, the formula that we're going to use for this, and we're asked to find concentration of A, and we want to find out the value of K. So, a couple things we've got to go after. Well, let's start with the formula that we're going to be using here, which is A is equal to A0 times 0.5 to the n power, the world's worst making formula. We need to find out that n. The n is the number of half-lives. Well, how do we find the number of half-lives? Well, this is going to be the total time, which is measured in seconds or whatever, divided by the half-life, which is the time per half-life. And so if this is like seconds and this is seconds per half-life, the seconds cancel out, and the half-life is in the denominator, and so this will give you the number of half-lives. So this is another formula you should put into your chemistry toolbox. Now, so let's plug in this stuff here. So the total time here is 1 hour, which is 60 minutes. So we're going to need to have the same label, so I'll go 60 minutes. Now we could change it both to seconds, but it's really not necessary until we get to the K part, which should be expressed in seconds to the -1. So we'll just try to get the same one for them. So N is going to equal to the total time, which is 1 hour, so 60 minutes, over 14.0 minutes. You see, that's per half-life. So the minutes cancel out, that means half-lives. And so when we work that out, you get 4.29 half-lives. Well, that certainly wasn't one of the options we had in the last assignment when we had perfect whole numbers, 1, 2, 3, 4, 5, and so on. Now we got 4.29. So this is why this formula has become very important here. We can take that right there for that n there. So A equals, or the concentration of A, what we'll call this now, since we're doing concentrations, is equal to the original concentration, which we said is 4.5 grams, times 0.5, and now N is 4.29 power. We punch that into our calculators and we get an answer of 0.230 grams. So, 0.230 grams is what we're going to get out of that. Now, technically not a concentration, that's most clear, but it's the same basic idea. If it was in solution form, we'd have that, and in mass form, we'd just say A or concentration A. So that is, we're quibbling over little things. So I'll just put an A there since technically that's not a concentration. Okay, and that's what we have up there. Now, we haven't finished yet, we haven't found K yet, so we know that K is found in the half-life formula, which is T1 half equals 0.694 over K. And in arithmetic, we need to get the K out of the denominator. You got to be careful on this. Don't divide both sides by 0.694. That still leaves the K in the denominator. Two ways we can solve this. We can put a 1 under this and cross multiply the K by itself, or recognize that in problems, in algebra problems like this, when you do the proportional setup, you actually are ending up just switching those two around. So K is equal to 0.694 over T. Put an arrow there. Oh no, we'll just leave that because that will solve the K. That's 0.694 over And the time we had for that was 14 minutes. But we don't want minutes, we want seconds, so we'll treat this like a conversion problem. Put a time sign there, put minutes on top, seconds on bottom, 1 minute and 60 seconds. And we should get 1.77 times 10 to the negative 3, and minutes cancel out, we have seconds in the denominator, so that's s to the negative 1 power. So that's how we find the values there. So two powerful tools here. Using this formula right here, you could put another formula in there for respect to k if you want, or just use your algebra skills and keep that same formula you had before from the last unit. And the other one is, of course, this one, n equals t total over 2.5. Next one,